GeoAI is transforming the way we work with spatial data. GeoAI, you can extract features such as buildings or roads, in this example from the country of Grenada. You can unlock data buried inside PDF reports, get it in your GIS for downstream analysis. You can automate analysis, such as in this case from Australia, performing vegetation encroachment analysis around utility power lines. You can make better predictions given historical data, and you can derive various kinds of insights, such as by performing damage assessment after a hurricane. The pre-trained models on the Living Atlas are making GeoAI easier and more accessible than ever. You can use them as is for your tasks or fine-tune them to your geography or features of interest. There are over 100 models now, including models from Esri, models from distributors around the world, as well as models contributed by some of you sitting in the audience. So thank you for that. We have recently integrated ArcGIS with the Hugging Face Hub, which is home to thousands of open source models that you can now use just by providing their ID in bridge or adapter models that we've recently added to the Living Atlas. And while pre-trained models are powerful, many of you need to train your own models or customize them for your geography, your data, or features of your interest. And this is especially true for specialized use cases, such as identifying species or habitat mapping, where your domain knowledge and the local context matters. ArcGIS provides many tools and experiences across ArcGIS Pro, Enterprise, and Online that you can use to customize these models and create new GeoAI models for your needs. And in case you want to use an open source model or want to connect to a cloud-hosted model, you can do that as well using Python inferencing functions. And then just use these tools to connect to these and integrate with these models. Now, let's hone in on imagery. This is an area where GeoAI really shines. ArcGIS supports extracting meaning from a wide range of imagery sources, including overhead, aerial, or satellite imagery, to multispectral, and more recently, hyperspectral imagery, to 3D point clouds and videos. We've recently integrated remote sensing foundation models, models that you might have heard of like Prithvi or the Clay Foundation model, that you can now readily fine-tune on your tasks using a limited or just a handful of data. To see some of these capabilities in action, let me hand it over to Priyanka.
Thank you, Rohit. Today, we are demonstrating how GeoAI transforms imagery into operational insights. Hurricane Melissa, a Category 5 storm, swept through Jamaica last year. When such disasters occur, responders must quickly identify which roads remain accessible and where damage has occurred. Our immediate mission is to deliver medical aid from a helicopter landing zone to 2 priority locations, a hospital and a relief tent in Westmoreland. Many roads may be blocked, flooded, or damaged. We cannot rely on pre-existing road data. So we begin by rebuilding our transportation network from imagery. Using the road extraction global model from the Living Atlas, we detect roads directly from post-disaster imagery. Next, to assess road condition, we load the vision-language context-based classification model from the Living Atlas into the Classify Objects tool and categorize these road features into these classes: completely blocked, minor debris, major debris, or clear. We also provide additional context to the model so it knows that this imagery is from Category 5 hurricane. And here are the results. A classified road layer that shows current road conditions. The roads that are classified as blocked, such as this flooded one shown here, can be used as polygon barriers for routing. Using the updated road network, we performed routing analysis, where the helicopter landing zone was our starting point, and the hospital and relief tent were added as stops. The system then generated the optimal paths to reach both of these priority locations, avoiding blocked roads. And in minutes, we moved from raw imagery to operational routing. Next, let's focus on debris that needs to be cleared up. This can help with inefficient allocation of equipment and resources. This layer that shows debris was not manually digitized. It was AI generated by fine-tuning a remote sensing foundation model named Dynamic One for All, or DOFA. Since this foundation model already understands the spatial structures and the spectral patterns in imagery, we required less than 100 training labels to fine-tune it. And within 30 minutes, we got these results. That's the power of foundation models, dramatically reducing the need for training data. Now, we also need to understand which buildings are affected and how severely. To achieve this, we leveraged these user-contributed models from the Living Atlas: roof hole delineation and roof decking delineation. On the models item page, you can see its detailed description, input requirements, performance metrics, and so on. The models page also links to the GitHub repository, where the training workflow and implementation details are also documented. Using the provided notebook, I fine-tuned the model on this post-disaster imagery and was able to quickly adapt it to our study area. And finally, I generated this building damage severity layer that highlights areas of visible structural impact and also the severity of the damage. When disaster strikes, time is of the essence. GeoAI delivers rapid, scalable analysis, transforming data into action when every minute matters. Thank you, and over to you, Rohit.
Thank you, Priyanka. So now let's look at another important data modality, unstructured text. Now, as many of you know, geospatial data doesn't always come neatly packaged as feature classes and file geodatabases. Often, the most valuable information is buried deep inside unstructured text, PDF reports, incident logs, articles. And that's where GeoAI for text comes in. ArcGIS has tools and pre-trained models to unlock geospatial insight from unstructured text. You can use them to categorize text, extract entities and locations from unstructured text, or transform it in various ways. And recently, we've added the ability for you to use large language models with these tools to perform a wide range of tasks. To see some of this in action by unlocking data from PDF reports, let me hand it over to Shivani.
Thanks, Rohit. We often work with long technical reports like this. This is a 171-page geotechnical borehole report containing coordinates, elevations, depth tables, and geological descriptions. Instead of manually extracting this information, which can take hours, we can automate it using process text tool in ArcGIS Pro. Here, we point the tool to our input folder containing our borehole PDFs. Next, we bring in a custom deep learning model, or DLPK. This DLPK holds our specific prompts and extraction logic. Finally, we give it a connection file. This connection file contains our API keys, allowing the tool to securely reach out to foundation LLMs, whether these are hosted on Azure or Amazon Bedrock. Running this tool will get us 26 boreholes. Also, we get 1,278 data points, their depth intervals, and descriptions in a couple of minutes. We convert these extracted data and convert this into a voxel layer, creating a continuous 3D subsurface model. As I move along, the voxel clearly shows the underground layers, exactly where the tunnel boring log will encounter different soil types. As developers, you are probably asking, how do I build this for my own messy reports? The engine behind this is our custom deep learning package. This is essentially a zipped folder containing two files: Esri model definition, which tells ArcGIS where to find the custom logic, and a Python script where the real work happens. To build your own custom processor, you need to write three main functions. First, a function to read those API keys and connect to the AI connection to Azure or Bedrock. Second, you define your prompt. Also, tells ArcGIS Pro which fields to return, like from depth, to depth, layer code, and description. Finally, the predict function. Here, we add our Python logic to pass the PDF along with the LLM prompt, format the response, and hand a clean dictionary right back to ArcGIS Pro. Think about the paradigm shift here. With Python and a well-crafted prompt, you can transform complex, unstructured documents into living 3D spatial information. The barrier to extracting information and the unstructured chaos has never been lower. Over to you, Rohit.
Ani. Thank you, Shivani. OK, so we've seen how GeoAI works with different kinds of GIS datasets and helps you automate several tasks. But GeoAI is changing. We are now seeing the emergence of foundation models. These are large-scale, deep neural networks, often with 1 billion or more parameters, that are pre-trained on broad and diverse datasets, often multimodal datasets, in a self-supervised manner. That means without even any labels. And these models learn to distill the signal or the meaning of that data in the form of what's known as embeddings. This is a series of numbers that capture the signal and distill the information from that raw data. And then lightweight methods can be used to readily adapt the model to these various tasks. At Esri, we are uniquely positioned to drive innovation in this space by leveraging our deep geospatial expertise, authoritative Esri datasets, and flexible deployment options across ArcGIS. And as part of this work, we are developing our own geospatial foundation models, including a Geo-Demographic foundation model and a Geospatial Vision-Language Model. Both of these are in active R&D, and we are working to make them available for use within ArcGIS. Esri's Geo-Demographic foundation model is a kind of a location embedding model. It learns to represent each location or coordinate in the form of these geodemographic embeddings, which capture from that training data what it's learning, which is demographic data, such as the US Census or American Community Survey, maps and layers of economic activity, environmental data, how urban or rural a place is, and so on. And the embeddings that are produced can be used for instant similarity search and change detection, or in combination with your data to help make better predictions. The geodemographic embeddings produced by this model represent each place as a series of numbers that computers can easily process to perform similarity search and pattern recognition. And in the map here on the right, we are visualizing just the 30th dimension of the geodemographic embeddings. There are over 200 dimensions that are produced for each of the nearly 2 million hex bins at the H7 level across the United States. These embeddings go beyond the latitude and longitude of a place and capture the socio-economic, demographic, and environmental signals from that training data into a vector of about 200 numbers. And they enable better predictive modeling and power advanced geospatial workflows like finding similar features or filling in missing data when, like in the real world, data isn't perfect. There's always gaps. And you can use this model to intelligently fill in those gaps. To see the power of Esri's geodemographic embeddings and the tools we are adding for embeddings-based analysis, let me hand it over to Karthik. Over to you, Karthik.
Thanks, Rohit. We are looking at the neighborhoods around Greater Los Angeles area. Each point here represents a block group with an unknown median housing price which is waiting to be uncovered. And for years, we have tried to predict these prices using the well-known explanatory variables or the predictor variables, such as the median age of the homes, the total number of rooms, the total population of the block group, and so on. And these predictors do a good job, but only as good as the information they contain. Now imagine if each of these locations could whisper something deeper, something which the raw predictors cannot show us, patterns that are spatial, subtle, and hidden. That's what embeddings bring to the table. So here's what we did. We trained our first model using the same old predictor variables, and we used a gradient boosting model for this purpose. This gives us a solid baseline. So we trained a model and got the predictions on a test data set, and here are the results. You see some points which are here in yellow, where the predicted prices are within 5% of the actual prices, which is good. But as we move across the map, we see the error starts to widen from 5% to 10%, 15%, sometimes more than 20% as indicated by the red points here. We now bring in our embeddings, which are generated by the Geo-Demographic Foundation model. These embeddings are generated at hex bin H7 resolution level, and each of these hex bins spans across an area of approximately 2 square kilometers. Each of these 1.8 million embeddings spanning across the entire United States is a spatial signature that captures the census, demographics, environment variables within these fixed set of numerical values. So we take this original data set, spatially join it with this particular layer, and then we retrain the model. We use the same model, same hyperparameters, no tuning magic. It's just that each of these locations now have an additional layer of spatial intelligence which I did not have the access to before. So we train again, test again, and the results change. You see some of these points which were here in the darker shades of orange and red have started to fade into lighter shades of orange and yellow. This indicates better performance. The test R-squared value has improved by about 15%. So what happened? The embedding supplied our models with an additional context which the raw predictors couldn't provide. They distilled the surrounding geography into something meaningful which the model could really understand. Patterns of similarity, neighborhood structures, spatial relationships, these are all hard to capture, but that's the foundational power of these embeddings. And they don't replace your predictor variables, but they elevate them, turning ordinary models into spatially aware ones, and ordinary predictions into meaningful insights which are much closer to reality. Now let's turn our attention towards some of the tools that we have been working on to work with these embeddings. Under the Analysis tab, there's an embedding-aware workflow, which is designed to help you find meaning in your data. It offers 3 tools. 1, the generate embedding using AI model tool, which allows you to use any of our foundation models to convert your raw data into embeddings. When you want embeddings for a much larger area than what you currently have, the merge embedding tool comes in. And then the third one, the find similar tool. So let's have a closer look at this find similar tool using something visual. Here's Bradenton Beach after Hurricane Milton. I can simply click on some signs of damage, like this scattered debris here, and there's one over here. And the tool immediately finds the regions which are similarly damaged. No labels and no training data. It's just the vision embeddings capturing the visual patterns and highlighting the clusters of damage with just a glance. With just a couple of clicks, we were able to turn these two observations into a map of insight. But let me tell you what's going on underneath. We have divided this entire extent into this rectangular grid like this, and we have pre-computed a vision embedding for each of these grid cells using a foundation model from Meta called DynoV2. This particular model is great at capturing the visual patterns in high-resolution RGB imagery and storing them as these embeddings. When I select a pattern or an object to search for, the tool scans across the entire grid and finds and highlights those grids whose embeddings closely match my selection. OK, so that was similarity search using vision embeddings. Now let's turn our attention towards something completely different. We are going to look at finding similar high disposable income regions in Orlando. I'll continue to use the same tool, but I'm going to provide it a feature class which contains a Geo-Demographic embeddings. Recall that the Geo-Demographic embeddings are captured at hexbin H7 resolution level, and I provide this one location with high disposable income, set the similarity threshold to about 0.9, and the tool immediately highlights similar locations with high disposable income. And it's no surprise that the tool is able to do this because we used Geo-Demographic embeddings, which were generated by a model which was trained on census, demographic data, among others. The next use case, however, is a bit more intriguing. And we are going to do this analysis, the similar analysis, at a much larger scale, in fact, across the entire country. To do this large-scale analysis, I'm going to use a geoprocessing tool, find similar features using embedding. Feed this tool one reference location, like the Arizona State University, and the tool scans across the entire search space to find other location with similar embedded signature. It's like saying, find me all places which feels like this, and the tool delivers consistently and objectively. We are looking at the results here from the search. And notice that this particular model was never specifically taught on how to identify the university towns. But it was able to find, the tool was able to find a demographic pattern in my search location and use the embedding to find other locations with similar embedded signature. And what's exciting is that imagery, text, location, they all go through the same embedding workflow. Disaster response, market analysis, site suitability, if it exists in space, it can be embedded. And if it can be embedded, it can be compared. And with it, we open doors to insight which we have never been able to capture before. Thanks, and over to you, Rohit.
Thank you, Karthik. Yeah, that was awesome. OK, so now let's talk about Esri's upcoming Geospatial Vision-Language Model, or GeoVLM for short. This is like a Swiss Army knife for many remote sensing tasks. It connects satellite imagery with natural language. It's really a multimodal LLM that knows about imagery and can perform various tasks, such as segmenting roads or buildings or other features, just using prompts, or describing what it sees within an image, or region or answering questions about imagery. To see these powerful capabilities of the upcoming Geospatial Vision-Language Model, let me hand it back to Shivani.
Thanks, Rohit. GeoVLM can do multiple tasks, such as detecting and classifying objects, answering questions about imagery, and describing what it sees. Here, I've loaded our GeoVLM model in the Detect Objects using Deep Learning tool. Let's start with something simple. I can give the prompt to segment trees. In the interest of time, I've already run the model, and here are the results. Similarly, we can detect buildings and roads. GeoVLM breaks the paradigm of needing one dedicated model for each of these tasks. Also, without any region-specific tuning, we can work across different geographies. Here are the results from Zimbabwe, Las Vegas, and Austria. Different landscapes, different imagery conditions, yet the same results across everywhere. Now, let's look at GeoVLM's open set capabilities. I can ask the model to detect windmills, and we get the detections. Similarly, storage tanks. Again, the model was never trained for any of these objects. The model recognizes these simply by using their shape and spatial context. So this was all about detecting objects. Now let's look at model's question-answering capabilities. Here, I'm going to use classify objects using deep learning tool. And I'm asking a question, is there new construction in this area? At this point in time, as you can see, there is new construction and new development in this area. So model detected and responded with construction site detected. As I switch to the latest imagery, as there is no construction anymore, the model correctly identified and it said no construction sites. The model also excels at generating scene descriptions. Here, I ask, what do you see? And as I click, the model has generated a detailed description of the scene. It highlighted the red and green color scheme, the filled-up parking area on both sides, and also the text, Texas Tech. GeoVLM can also be used for scientific workflows, like glacial lake monitoring. When I prompt GeoVLM to segment glacial lakes, it clearly identifies them. Then, when I ask, are these lakes snow-covered? It instantly identifies their state. With these results, we can even perform further downstream analysis. Similar to other foundation models, GeoVLM can be used to generate embeddings. These embeddings can later be used to perform search on the basis of text. Here, I asked the model to detect container cranes. And the system immediately highlighted these using the text and the imagery. This was a sneak preview of our upcoming Geospatial Vision-Language Model. By bringing together vision, language, and geospatial understanding, GeoVLM opens new ways to interact with imagery. Over to you, Rohit.
Thank you, Shivani. OK, so that was a quick tour of GeoAI across ArcGIS. We saw how GeoAI turns imagery into operational insight, how you can unlock data from PDF reports and get it in your GIS, and how we are innovating with geospatial foundation models like the Geo-Demographic foundation model and the Geospatial Vision-Language Model. This combination of AI with GIS is very powerful. Not only can you use it to let AI take care of the drudgery of work like feature extraction, but also use it to solve some of the most complex challenges facing the planet.